Afternoon, gentlemen. The good news is we're running early. Good news for me. Bad news for you is we're running early. So that's going to give me a good amount of time to talk to you today about Coax. And I'm a very happy man because Coax as a subject I find fascinating. I think I can make it interesting for you. You'll judge me at the end of this presentation. So I'm happy because I'm talking about Coax. I'm the fifth of 5 presenters. The other 4 presenters have already done half my work for me. Gives me a great amount of time to enjoy the presentation with you and introduce some interesting things that I don't think you'll be aware of. Now, I know a few faces, and I'm guessing that the majority of you folks are not RF people. So Coax is something that doesn't necessarily cross your bows too often. That's good. So let's roll into this presentation, and we're going to start off with a confession here. As Richard said, I love Coax. I do really love it. It's not like fish and chips. I mean, I like fish and chips, but I love Coax. Coax for me is the real thing. So, what is coaxial cable anyway? Coax has been mentioned in all these presentations so far. A lot of good information's been taken across. But I guess if I asked everyone in this room what coax cable is to them, they'd come back to me with 1 of 4 answers. So I'm going to try and anticipate each of the 4 answers you might give me as an answer to this question. Now, your first answer might be, hey, I know what coax is. It's that crummy brown cable that comes down off my roof from my antenna, bangs against the mast in the wind, and that crummy brown cable coming down from the antenna has been up there for years. And before the antenna fell over, there was another antenna up there, and it was there for years before. So that's what coax is. It's the brown cable that delivers my television pictures. Another answer might be that you would say, well, no, actually, it's not a television aerial cable, it's a satellite cable. It's not brown, it's black. Now, this black satellite cable has fairly recently come into my home. Might even be a second one with it if we want to be in the position to record our services. So the answer to the question might be, well, yeah, coax is a black satellite cable. Different connector, interesting. Another possible answer might be, and this is the sort of answer you'd get from maybe an AV guy, maybe a fibre optic man, a Cat5 man, maybe this new generation of 4G suppliers, these whizzy guys who want to deliver all our content through the air. Now, they might say, well, coax is old. It's practically finished. Why is it still here? Why are you still using coax? Coax to these folks is the one thing more than any other that represents old television technology. Fourth answer. Now I've put here it's new technology. What I should say, perhaps more accurately, is it's current technology. Okay, imagine a situation. You wake up one morning, all the coaxial cable in the world has disappeared. We've got all the source material, we've got all the screens, and we've got all the TVs. No television. What's going to happen? I'll tell you what will happen. The engineers around the world will say, what are we going to do here? They'll put to work, and what will happen, they'll get together, they'll decide what has to be done. By the end of that day, all the engineers will have said, we've sorted the problem, we've solved the issue, we've invented something called coax. It's what's going to happen. It's current technology. So, again, as coax cable is maybe not so familiar to you, you know it generally, you don't know it specifically. In this presentation, we're going to jump and dart all over the place. We're going to hopefully keep it interesting, mix it up a little. So let's look at coax in a little more detail. And let's note several aspects of coax that maybe haven't been obvious to you. A lot of people think coax is a single core cable with a shield or a screen. Well, it isn't. It's a twin core cable. The second of the two cores just happens to wrap round the first, and we've got an equidistant space between the inner and the screen. So it's actually quite a clever cable. It's a self-screening twin core cable. If we look at the shielding, we see the shielding on the best coax cables out there is made up of a tape, a foil tape, and a woven braid. And the reason for that, apart from superior screening, is the fact we rely upon the foil to be the better screen where the cable remains unmolested over long distances. And we rely on the braid to plug the holes up when we start connecting things together and start working the cable, moving it around and splitting the foil. We're going to make the assumption on this piece of cable that the centre conductor has a diameter of 1 millimetre. And we make that assumption because it's easy. 95% of the coax cable out there, probably all the coax cable you guys have ever come across, is of that type. We call it a sub-feed, a subscriber feed, a user feed. So it's the small cable that goes into the simple connectors into the back of the devices we're connecting it to. We're not going to over-concern ourselves now with larger types of cable. So 1 millimetre inner core, and we're going to visit this 1 millimetre inner core cable as we go through the presentation. Final thing, and I think the most interesting thing about the coaxial cable as a structure, is the dielectric material. So that's the material, foam, airspace. You've seen that material. It's packing the centre core, holding it accurately within the middle of the shield around it. Now that dielectric material, okay, expanded foam, is a solid or airspace with those tubular spaces of air that run through the polythene when you look end on. That performs more than just an insulating function or an electrically neutral function. It does all sorts of things that help us with our cable, help us with the design and the performance of our cable. So it's not the best material, I have to say. The very best material we could use in place of that dielectric would be fresh air. That gives the cable boys a big problem. We specify fresh air as the dielectric between the inner and the outer. It's going to be an issue. Can't have it. Pity, be rather nice. Would make the coaxial cable even better. So, everybody knows what it is. Some people know it well, some people work with it often. Few people know about its origin, and we're going to explore that today. We're going to look at the origin of coax, because, as I said earlier, it's actually very interesting, really quite entertaining. Why is it important? It's important we know, because we need to be telling people, and we need to be promoting the benefits of this cable going forward, so it's not half a bad idea to learn a little more about it. Okay, let's go back to some basics here. We're going, first of all, to look at the electromagnetic frequency spectrum. This is nature's frequency, all the way from nil hertz at very nil hertz, which is of course DC, up from the very bottom there into the sound frequencies, where we have very long wavelengths, through the area that I've called radio waves, which is the area of frequency, the area of signals that we carry on our coaxial cables. Of course, we can go up out of the range of a coaxial cable frequency, and we can go into all sorts of other areas. And I've picked various energies, various frequency energies, lights hanging on in the middle there, and we go to tiny wavelengths we go to fractions, we go to nanometers, we go to fractions of nanometers. So we go to tiny wavelengths. To put the whole wavelength thing into perspective, if we go down to if we take a piano keyboard, let's go down to the bottom of the frequency range. Piano keyboard, bottom note on a piano keyboard has got a wavelength of somewhere in the region of about 10,000 kilometres. That's quite a long wavelength. Top note is still tens of kilometres. We're going to look at the frequency spectrum of coaxial cable. We're going to look at those wavelengths and those frequencies and put it in some sort of context with those huge wavelengths of those very low frequency sources. Okay, spot fact. F connector. Everybody knows the F connector because it's what we said right at the beginning was what someone would say is a satellite cable. But the surprising thing about the F connector, the so-called satellite connector, is it didn't come about as a result of satellite, the needs of satellite dishes. It was around a long time before satellite cable, satellite requirements. The F connector was invented in the very early 1950s in the US. And it was invented, as I've put up on the screen there, as a reliable connector for the emergence of the post-war cable television boom that started in the States. So the F connector's been around 60-odd years. Unbelievable. We've only been seeing it for the last 20, 25 years, but it was around way before then. So the satellite connector was originally a cable television connector. Let's go back to the frequency range there, because now we've squished the frequency range into a much smaller area, and it's the area, Jason said earlier, the area from about 5 megahertz up to 2 to 3 gigahertz, which are the frequencies, the modulated frequencies that we can carry on a coaxial cable. And what I've done is I've just added in the various interesting elements across the frequency range. So, for example, in the middle there, digital terrestrial broadcast, we call it DVB-T, basically the UHF band. It's where we will choose to allocate the signals that we are creating on our ZeeVee digital modulators. If you go down the frequency range, you'll go through some VHF bands, normally populated by the cable TV guys. You'll eventually go through DAB digital radio onto FM radio. You'll go into some return path and comms frequencies before you eventually end up at the lowest frequencies that we carry through coaxial cable, which is old AM radio signals. Top of that band there, it says DOCSIS in blue. DOCSIS, again, I think was mentioned earlier, and this is our internet data. This is where DOCSIS bands live on cable television systems. DOCSIS bands are now starting to appear up-band, up from the UHF area, up from the DVB-T area, where currently we are starting to give up some of our bandwidth, some of our frequencies to the 4G mobile providers. They're sort of chiseling away, they're coming in at us from the top. Up higher from them are the satellite F frequencies. These are the frequencies that come out of the satellite dish LMBs. These are the frequencies of our raw satellite signals that we switch and share around into our satellite receivers. Talked about wavelengths earlier. Here's an interesting fact. If we go to 300 megahertz, in the VHF waveband, the wavelength at 300 megahertz is 1 meter. I like that. That's pretty. I can get my head around 1 meter. 1 meter wavelength. Goes up the top, comes down, comes back to where it started. One wavelength, and it's 1 meter at 300 megahertz. So that puts, I think, some context into the frequencies, into the audio frequencies. If you go down to the bottom of the band there on AM radio, we all remember Radio 1 was 247 metres, something 257, Luxembourg 208. That's the wavelength of the frequencies in the AM radio band. So there's our clutch of frequencies that we are handling on our coax cables, and that's basically what they do and where they sit in our services. We're most interested in the UHF DVB-T bands. Okay. Another spot fact, dish antennas. Dish antennas, they were invented 25 years ago, quite obviously, for the start of satellite television, because up until that moment, it didn't exist. Well, do you know they did? Because if we go back to the early war years, the very early 1940s, a British engineer invented a thing called a magnetron, which made it possible to generate very high frequencies, very high VHF, UHF frequencies for the first time. And the only antenna that would be suitable to handle those, to both transmit and catch those frequencies, was the dish antenna. So the dish antenna, satellite dish if you want to call it, was invented 20 years before satellites. Interesting fact. Okay, let's go back to our 1mm cable again. Because what we want to do now is understand loss. And the presenters before me, they talked about loss, and they talked about simple networks, and we'll put a simple network up, but we'll go into it a little more to understand it a little more, I think. So what we've got here is our 1mm inner core cable. Now we need three factors to know and understand the loss of this cable. We need to know the frequency of the signal that we're running through the cable, because as you can see along the bottom line, when we plot it against the loss in dBs on the vertical line, we'll see that the higher the frequency, the greater the loss. I think we know that anyway. Explain why a little later. So loss decreases as the frequency decreases. So when understanding the calculation of loss on a coax network, we need to know the frequencies that we're putting through the cable. We need to know the diameter of the inner core, because it tells us the loss at those frequencies. And for ease, we look at 100 meters as being a specific cable length. So we look at the graph, and we look down around about 860 megahertz on the bottom line, run the line up, and at that frequency, which is UHF channel 68, we see that the loss on this 1mm cable is around about 20 dBs. Simple rule about loss. It's a voltage-based measurement, and therefore the 6 dB rule applies. So if we take a spot frequency, generally anywhere on the curve, and if we halve or double that frequency, we'll find that the loss follows the 6 dB rule. Double the frequency, roughly speaking, 6 dBs more loss. Half the frequency, take 6 off. Doesn't work because, of course, the line's curved at the end. But it works if you take a spot across the curve. So we've understood, I think, our simple cable. We've understood its loss. We've understood how it handles the frequencies. And that's important for us to know if we're going to be working with the cable and working with the ZeeVee modulators and understanding what the televisions need to see at the end of the cable. So the next 3 slides or so are a basic overview of level and measurement. Now, I think Steve, right at the head, he talked about level and measurement. We'll talk about it a little more, but I won't go into it in an exhaustive way because it's a quick snapshot of the demonstration that we've got upstairs. So I'll introduce you to the basic concepts, which you can understand more readily if you want to go upstairs and look at our test equipment, our spectrum analyzers and our measuring kit, and you can see how it pans out for yourself. So this is by way of an introduction. Now, if you check the specification of the ZeeVee bridge modulator, it will tell you that the output level is 100 dB microvolts. Put it another way, it's 100 microvolts. It's 100 millionths of a volt. It's a tiny voltage. Interestingly, it's quite a high level for us in the RF domain. It's quite a high level. Look on the line on the left there, and you can see the 100 dB microvolts. If I approach the drawing, you'll see there's 4 multiplexes. We've put a marker on the multiplex on the far left, and if you look at the top of the scope, it'll tell you that's 474 megs, UHF channel 21. So you can see we've got 4 multiplexes containing 4 services on adjacent channels, and the output levels around 100 dB microvolts. Because we could use dBs as a ratio, we'll drop the microvolts, because we'll turn it into 100 dBs, and then we can more readily use it against our fixed losses for our system plan. It's that simple. Okay, next screenshot. Steve touched on this briefly on the first presentation. This is a constellation diagram, and this is plotting the accuracies of the modulation. So what we're seeing here, as Steve said, if we had intense white dots right in the middle of the matrix, we'd have little or no modulation inaccuracies or errors. But we haven't. We're dispersing those dots, so some of those hits aren't quite spot on. We've got some errors within the modulation process. Just above the right-hand template there, you'll see some figures, and it gives us some figures of our bit error ratios. It's more easily explained when we go on to the next slide, where we've got some bar graphs. So, here we go again. Channel 21 UHF. It's telling us that it's 474 megahertz. It's DVB-T. This is the modulation standard that we're working on from the modulators. This is the modulation standard that is our Freeview and our Freeview HD standard. Against modulation, it's confirming 2K. What that means is there are 2,000 carriers packed into each multiplex. And all those 2,000 carriers are all carrying the same information. It makes it very robust. So we've got an 8 megahertz wide multiplex, 8 megahertz wide channel. Below that, under modulation, continuing on from the modulation, we show 132.78 there, the code and guard rates. Don't worry about that. Basically, our modulator's set to maximum smoke. That's what that means. So, briefly, looking at the green bars, topmost of the 3 clustered together is our measurement of bit error ratio before we perform the error correction. So we're showing 1.4 errors to the -5. So 1.5 errors in 10,000 bits of information. When we apply error correction with our measuring device and with any device that's happening to receive this signal, that will actually become a much better signal. It's not that bad in the first place, to be honest. But with bit errors corrected, we're up to about 9 errors in 100 million bits of information. Immediately below that, PER, packet error ratio. That's absolutely fine. The line at the bottom is quite interesting. The MER, and a couple of folks have talked about MER, can be quite a contentious subject. MER, you measure MER and have a figure. It's a bit like asking someone the time. They'll tell you the time because, as far as they're concerned, their time is correct. Fact is, and it's upstairs for you to see, we've got 2 measuring instruments. And they both give a slightly different bit error rate. Sorry, MER. They both give a slightly different MER. Again, you have 2 watches. You look at the time, which one's right? And the answer to that question is the same as the answer to the 2 modulators upstairs. Which one's right? The answer is they're both probably wrong. Okay, we won't worry about that because generally speaking, they're similar. Generally speaking, they're right. Generally speaking, because they're simple bits of test kit and not bench kit, they'll probably be reading low. The actual MER is probably in the middle 30s. Before we move off this slide, the one key thing about this is this particular device, bottom right-hand corner of the matrix there, says NM 9 dBs. What that means is noise margin. And what that is telling us is the MER and the elements that have created that MER, the errors in the system, the noise margin on that is 9 dB. So 30.5 dB MER is great. We could erode that great MER figure by 9 dBs before the signal falls over. So we've got 9 dBs of stuffing in that cushion. We've got 9 dBs of benefit. And 9 dBs may not sound much, but trust me, 9 dBs of noise margin on the signals we've created is enormous. It's magnificent. It's great. We've got to go some to trash that signal. So it's very robust. I'll talk more about that a little bit later. So coming back onto slides we should concern ourselves with now. We talked about the cable. We've talked about the measurements. So now we're looking in a little bit more detail of a coaxial plan. So what I've shown here, the source is the ZeeVee modulator on the right. There's the 100 dB microvolts. We'll call that 100 dB, maximum out. We know the loss of the passive elements. We know the loss of the splitters because they're stamped on the label. We know the loss of the cable, assuming we're using 1mm inner core, and we will be. So we can now quite accurately watch this falling signal level as we pass through the passives of the network. Interesting point here that no one's measured is the threshold of the TV. Now I'm picking 60 dB microvolts as the minimum input. It's actually much better than that. I think Jason, he mentioned a figure of 70, 80 dBs of link budget available. And we could get close to that if we lifted our launch level and we allowed that minimum level to drop lower. If this television was operating in a quiet room, away from a hostile RF environment, we could easily achieve a robust, successful signal as low as 40 dB microvolts into the television. We want to give ourselves a little bit of protection here against interference, impulse noise, anything that might come into the cable or interfere with the signal. So we're going to pick a minimum input level of 60 dB. So we've got 40 dBs of link budget. It's very conservative. We've actually got a lot more. Where we have bigger networks, very large networks, we can use simple amplifiers. On the right-hand side, we can put simple RF amplifiers in. They come in all sorts of shapes and sizes. They're all very reasonably priced. And they'll give us gains. Interestingly, our gains, amplifier gains are measured in dBs, makes things even more easy for us. So we can lift that level at any point, provided we operate any amplifiers comfortably within their dynamic range. We can amplify this signal endlessly. We can optically convert the signal. We can send it kilometres through optical fibre, retrieve it at the other end. Remember we had 9 dBs noise margin. Even if we cascaded endless amplifiers and we overran some and we underran others, we'd be pushed to be reducing that noise margin. Final important point here, I show the antenna in the circuit. More often than not, if you're inheriting a network, it's already got an antenna on it. If it hasn't, you've got the option to add the off-air channels. Now, what's crucial here is our measured MER on the output of our modulator is very good. Now, the transmission authorities, the BBC, they have better MERs from their modulators at the transmitter sites. And even when they power amp them, send them up to the top of the mast, the MERs are still better. Then they make the mistake of throwing them into the air, And what happens then is these signals bounce all over the countryside, they bounce off buildings, they reflect everywhere, they skip off the ground, they skip back down out of the upper atmosphere. They're affected by all sorts of environmental and weather conditions. And basically what happens to these multiplexes, they get trashed. The errors increase, the error ratios can be quite bad. So you can be quite sure that in 95% or more of all occasions where you've got an antenna connected to your system, that source material, those services, are significantly poorer than the ones we've generated. So if they're working on the network, we're so safe. It's that easy. The aerial guys do the hard work, clawing a decent quality signal out of the air. Their multiplexes aren't nice flat tops with a pretty square sides. Their multiplexes line up on the spectrum analyzer like a row of broken teeth. They can be quite badly damaged. They can be quite near the edge. So if they're getting it right on our network, we're laughing. We're catching a free ride. Encouraging, I think. So we're still on Coax. Coax is inextricably linked to things like antennas, and I'll show you how. Half-wave dipole, simple rod antenna. What it does, it gives us a characteristic impedance. We talked about this, I think this was touched on earlier. 75 ohms is the characteristic impedance of TV receive coax. 75 ohms. Why is it 75 ohms? Well, it's 75 ohms because the dipole rod antenna we've connected it to is giving us that characteristic impedance. Because we're using the cable as a feeder for that, we need to match the cable to the feeder. So these characteristic impedance needs to be accurately carried through all the interconnects in the chain between source, whether it be a ZeeVee modulator or an antenna, all the way through to the TV tuner. And a half-wave dipole, which is what that is, at 600 megahertz, bang in the UHF band, gives us those millimetric measurements, something like that. You'll say, hey, do you need the aluminium tubing? Do you need the aluminium rod? The answer's no. You can make an aerial out of the cable. All you've got to do is pull the inner and the outer apart to those precise distances, and your cable is an aerial. Simple. So another spot fact here, more dates. You'll notice this is getting older all the time. Coax is getting older. So we're back now to 1926 when our two Japanese friends, Mr. Yagi and Mr. Ude, interesting story about Mr. Yagi and Mr. Ude. Mr. Ude was the engineer, and Mr. Yagi wrote up his report. That's why it's called a Yagi aerial. Lesson there, I think, gentlemen. To be fair, Mr. Yagi was also an engineer. So what we're doing here, we've taken this simple rod and we've put it into what we perceive a television aerial to be. It's loaded with directive elements in the front, reflective elements at the back, and we've taken the simple rod, we've folded it back on itself. So what we've done in that antenna design, we have played havoc with the characteristic impedance all over the place. So there's a need now still to match the antenna to the cable, and we do that by putting a balancing transformer in the aerial box. If the aerial doesn't have a balancing transformer, must have a balancing transformer. Otherwise, the signal that you're struggling to claw out of the air isn't going to successfully transfer down the cable. Next fact, I love this. Coax plug, 1922. British invention, the coax plug, invented by a company called Bellinglee, long since out of business. It was invented for the sort of emergent radio, home radio antenna market. 1922. I love the fact that right now, all over the world, there are televisions being produced in factories in their thousands, if not tens of thousands. Every single one of them, barring a few, Every single one of them has got a 92-year-old connector on it. Fantastic. In truth, as good as the humble Coax plug is, not 75 ohms, it's less, it's not very good. Coax plug, it was fine for AM radio dipole antennas and the coax cable we lashed onto it in the old days, but to be honest, it's not very good. Thankfully, it's the last point of connection before the TV tuner. Tip here, guys, for coax networks, don't use coax plugs and connectors and adapters. Not so good. Use F connectors, they're brilliant. Okay. Coax is so much more than a lump of copper wire. Okay, copper wire, that's what you use for an electrical mains cable, stranded copper wire. But the coax cable is different, isn't it? It's so much more than copper wire. It's what we call a transmission line technology. Coax is transmission line. What does that mean? Well, I'll give you a couple of examples of transmission line. Top right indication there is that ribbon cable. Do you remember in the old days when we bought tuners and receivers for our hi-fi systems? In the back of the box there'd be a piece of ribbon and we'd connect it across the 300 ohm terminals on our FM radio input. It's a transmission line. It's a cable that is an aerial. We talked about that earlier. There's all sorts of transmission lines, of which coax is one. Transmission lines can be found in circuit boards. When we're carrying very high frequencies through circuitry, it's better if we carry it by printing it onto the surface of the board and having a ground plane underneath. We carry it more efficiently. So, what exactly is a transmission line? Okay, it's an efficient means of carrying a very high frequency over a cable that under normal circumstances would struggle to cope with it. We talked about frequencies earlier, didn't we, and wavelengths. What the transmission line does is it allows us to carry frequencies that are sizable fractions of the... I'm going to mess up here. The frequencies we're carrying are tiny. The wavelengths are tiny. Frequencies are large, the wavelengths are tiny. And the wavelengths will be massively laid out across the length of the cable. Our cables are going to be quite long, but the wavelengths that we're passing through, the lengths of the waves are quite short. So we've got high loss there, unless we can efficiently carry it. And that's what a transmission line does. It allows us to efficiently carry very high frequencies. So if we were to draw up a piece of coax cable of any length and turn it into component form, it would look something like this. So there's three components at play here, three factors are at play on our piece of coax. First of all, the resistor. So the resistor just means we have resistance equally across all frequencies through the copper. There's an inductive effect on the path of the cable, and an inductor, of course, is in this instance is actually a resistor but tuned to different frequencies. An inductor will resist and will have higher attenuation at higher frequencies and will allow low frequencies to pass through. And that's exactly what we saw on our loss graph on the cable loss, you'll remember. We saw an inductive effect. Talked about the dielectric earlier, didn't we? Dielectric has an interesting property because that's represented by the capacitor. So the dielectric actually is the same thing. It's a frequency-dependent resistor, but it has the effect of encouraging, with low loss and low resistance, the higher frequencies. So it will resist the lower frequencies. And that's an interesting effect. That leads us on to something, another parameter on coax cable that is quite interesting and links directly back to its heritage. So it's basic. We're back to the 1 millimetre inner conductor now again. We're going to look at something called skin effect. Now, skin effect is something that has plagued a lot of the development of comms cable going way back when, as frequency was increasing. What happens as we pass ever higher frequencies through the inner core of a coax cable, the current density decreases. So instead of the current clustering down the centre bore of the solid copper, as frequencies go up, the current flow starts to push itself onto the surface of the copper. So we see the effect there on 3 examples where we're sending ever higher frequencies through the copper. So now the current, now the flow, wants to sit on or around the surface of the cable, on the skin of the cable, on the skin of the copper. So what it looks like on the coax cable itself is our high frequencies are now skidding about on the top, and because of the capacitive effect through the dielectric, they're tempted to go jumping off the cable. You've got to be careful here. We saturate that cable with too high a frequency. The skin effect is going to encourage the higher frequencies to clear off out of it. They're going to leak away through the dielectric. So skin effect plagues all cables, has plagued, it plagues very low frequency cables, interestingly, but not to no great extent. And skin effect, again, is taking us back to the dawn of coax and why coax came along. We're going to look at another coax cable now, one that you may not have seen before. This is a very special type of cable. This coax is called heliax or helical cable. This cable is primarily used for transmission purposes. We've got something like 57,000 mobile phone cells in this country. Every single man jack of them uses helical cable running up the mast from the power amplifiers into the transmit antennas. And you can see why. We talked about these high frequencies being attracted to the surface skin of the cable. When you look at the inner core of this, it's completely hollow and corrugated. How much surface area has that inner core got? It's enormous. So what we're able to do is bear very high frequencies very efficiently at very low losses, and we can carry huge amount of current, which is exactly what we're doing on a transmitter cable, on a transmission cable. A couple of other things here. We talked earlier about the dielectric material, you'll remember, in the cable, and we theorised that the best dielectric material was air, fresh air. We've actually got quite a lot of fresh air in the dielectric now, so we've solved an issue. We've made the cable even more efficient. It's got barely any dielectric, 2-3% plastic dielectric within that area of space. It's lightweight. In fact, I think it's quite artistic. This is a beautiful area where electronic engineering meets mechanical engineering, creates something quite special. Final thing you'll notice is the relative size of the inner core to the overall diameter of the cable. Remember, on the simple cable, it's tiny. There's a huge amount of dielectric. On this cable, there's hardly any dielectric at all, any dielectric space. And that's because this is 50 ohms, not 75 ohms. When you do the power transfer calculations and you put 50 ohms in the calculator, you get a much more efficient transfer of power, which is why we use 50 ohm coax cables for transmission purposes. Years ago, we used 50 ohm coax in CB radios, you'll remember. So heliax, king of coax. I can't envisage a time when this coax will not exist. How can it not exist? When mobile phones have become old technology, what's going to take over then? So let's keep on this timeline, because I mentioned skin effect earlier, and I mentioned skin effect as crucial and key to the existence and the creation of coax. And how's that happened? Well, we're going back in time, guys. Going back further in time, because coax cable not only predates satellite, television, radio, predates the dawn of flight, predates the first radio transmissions, it predates the motor car. So we've got a cable here that was built a very long time ago for a purpose we now use, and for a purpose that at that time didn't exist. What's going on? I want to introduce you to someone, hero of mine, Mr. Oliver Heaviside. Now, apart from having probably the flattest head in Victorian England and probably the most angry eyes, not an easy man to get on with, Oliver, by all accounts. But Oliver Heaviside, brilliant mathematician and electrical engineer, he invented coax cable. You'll like this. He invented coax cable. He patented the design in 1880, and he patented the design for the UK alone. What was he thinking? I think we know what's going to happen here, don't we? He patented it. Truth be told, it was a full 20-odd years before this futuristic invention started to come to people's attention as a useful cable for the emergent communications industry. Oliver, bless him, he did more than invent coax cable. He was a telegraph engineer. And here's the clue, and here's the key to coax: telegraph cable. Coax was designed for telegraph systems. We had in telegraph systems, you have hundreds of miles of cable and very low frequencies, but you still have a skin effect. You still need a transmission line. Oliver not only developed, invented and theorised a lot of things, he also did something that was very important that accelerated the technology surrounding comms, communications at this time. He took a series of very complex calculations that a guy called Maxwell some years before had created and put into volumes of literally volumes of work. He took these complex calculations. He spent years going through it, years understanding it. He applied all sorts of interesting calculus, and he reworked and revamped these complex calculations and turned them into a handful of much easier to handle calculus, such that people could more easily understand electricity and magnetism. And what he did effectively, if our friend Maxwell some years ago had created the seeds of this revolution by creating some sort of cobbled stone road, if you like, what Oliver did by changing these calculations and reformulating them, he dug up the cobbles, he laid a piece of asphalt, he straightened out the bends, he created a highway. And from that moment on, the achievements of the electrical advances that were made at that time multiplied. So he made things happen a lot quicker. Final note on Oliver, bless him. He was visited by a couple of American engineers in the very early 1900s who'd stumbled across his work on coaxial cable. Remember, it hadn't been built up to that time. And they looked at the work they were doing expanding the telephone system. And they said, we've got it, guys. We've got a cable that's ideal for this purpose. A cable that's going to massively increase the uptake of successful telephony. They travelled to the UK and they said to Oliver, you aren't going to believe this. You're going to be a rich man, they said. Because between you and us, we're going to take coax cable, we're going to sell it, we're going to sell it to the world, and we're all going to make a fortune. Oliver, bless him, mad as a hatter, he said, I invented coax cable. Unless I'm the sole inventor, the sole beneficiary, can't have it. Unfortunately, they did have it. They built it. They created coax, and then they laid the foundations of a telecommunications system, a telephone system that was then copied throughout the world. So poor old Oliver, brilliant mathematician, brilliant engineer, he missed out. He missed out on the marketing. So, coming back and in summary. So we asked the question, didn't we, at the start of the presentation, what is coaxial cable today? Well, I think we've covered enough and we've learned enough to say it's all those things, but more than that, coax cable is a leading edge, 134-year-old technology. So the guy who said it's old technology, he didn't know the half of it, did he? Yes, it's old, but it's brilliant. let's draw some conclusions. So, the speakers earlier talked about Coax's legacy. Coax has an overwhelming legacy. I think we're all agreed on that, but to give you some idea how much Coax is out there, I think one of the presenters touched on it earlier. B-Sky B, some years ago, year 2000, just before thereabouts, over a period of 10 or 12 years, pushed, cajoled, bullied, encouraged the industry to overwire, upgrade, rewire apartment buildings with coax cables. Around 4 million apartments were updated over that time period with brand new coax. So it's all there. It's all there. It's not old, decrepit. And as a result of that legacy, the guys who were pulling in these cables and connecting these homes up on these systems were also using the coax at that time in all other areas. They were using it in commercial buildings, they were using it in leisure activities, all the listings of networks and systems and commercial networks. So be sure there's a lot of very young coax out there. And that's before we even talk about the older coax. Remember, going back to the measurements, we had a noise margin, a very generous noise margin. We could possibly consider using some of that up on some older, less suitable cable. Possible. If we've got the spectrum analyzers and the test kit to monitor the degradation of the signal within comfortable limits, maybe we can use cable that isn't the best cable or the youngest cable. So coax, I think Richard said this earlier, coax has the lowest material cost per point. How can I prove it? I can prove it because I've said it. Therefore, it is a fact. I think you can understand and accept that. So, coax has a bandwidth that far exceeds structured wiring all through the air. And I think that's easily demonstrated by these tales of people migrating away from coax many years ago, finding they exhaust the bandwidth on their structured wiring, on their Cat 5, 6, 7 cables, and find themselves going back to coax. It's got a huge bandwidth. It's a simple construction. It exists in an overwhelming legacy. And of course, the through-the-air, the 4G services, they're struggling for bandwidth because they're pinching ours. They'll pinch more. They still won't have enough bandwidth. Still won't have enough bandwidth to hit all the mobile devices that are out there at the ever-increasing rates of data that they demand. So we'll always be ahead of the 4G through the air options. We'll always be ahead of the Category 5 structured cables. The only cable, the only method which we will struggle to keep up with is, of course, optical fibre. Because optical fibre is so far up the frequency range with nanometric wavelengths, there's enormous capacity available on optical fibre. But don't worry, because optical fibre is not suddenly about to be made available to the homes in the UK or into the commercial premises. Yes, it's gathering some momentum, but unless you live in Lithuania, which is the European country with the highest density of fibre to the home, fibre to the building, the rest of Europe's nowhere near any workable percentage, very low single figures. In the UK, I think it's something like less than 1% of buildings or homes are accessed directly through a piece of fibre. So fibre's not suddenly about to come on board and take over. Fibre will take a very long time to establish. So I now pull out one of my favourite sayings, and it was covered, of course, by Jason, wasn't it, in the Mocha presentation. And that is that all the technologies that threaten to make coax obsolete are being adapted to run on it. Makes sense. Makes sense. We're still using Victorian sewers. Okay, they pack up now and again, but they're still usable. Why do we want to change the coax that's embedded everywhere? It runs everything, it works everything. Finally, what we say is make the coax sale today while all the plucky contenders slug it out to take it on. After I wrote that, I thought about that again. And I decided maybe these plucky contenders aren't going to fight to take it on. Maybe one of them isn't the obvious right way forward. Maybe one isn't the obvious winner. It won't be all through the air. It won't come into the home unlimited bandwidth on the optical fibre. And the category 5 structured wiring won't be this panacea for all comms in the future. So all the competition won't actually be a winner. What will happen is that the competition, which is forming a tiny minority of the total amount that Coax achieves, that will slowly improve and increase over a very long period of time. And what will happen is these technologies won't want to take Coax on, they'll want to complement it. So it'll stay, it'll always be there. I was reading some figures, 2 minutes now guys, I was reading some figures published by Ofcom that related to the second quarter of this year, and they were looking at the percentage of homes that were continuing to watch television conventionally. And they found that 85% of homes continue and prefer to watch television on a big screen in a social environment, in the living room. Now, some years after the introduction of tablets and smartphones, you might have thought that was a lot less, but it isn't. We all still prefer to watch live TV, low latency, remember. We see the goal go in first and cheer before the next door neighbour's seeing it on his tablet. He knows what's happened. We found it first. So what's happening is Coax almost can't be taken away from us. It's got to be the best way. And everything else is going to support it. 28% of those people, to put things into perspective, said, well, yes, I'm in my social area, I'm in the living room watching my big screen TV. 28% said, yeah, but I've also got my smartphone or my tablet computer. I'm complementing the preferred source. I'm complementing the Coax. And I fancy these guys are going to complement Coax for years to come. So, I think you'll agree with me, if I've got it right, now we all love Coax. How could we not? Thanks, James.